The goal of this video is to provide you an intuitive and visual understanding of how the two main Earth-centered inertial frames are defined. And these two frames are the Earth-centered equatorial and ecliptic frames. So we'll be going over why they are different by a rotation about their common x-axis, how their axes are defined, which have to do with the rotation of the Earth and its orbit around the Sun, and why time is an important factor in defining these inertial reference frames. Now, the software I'm using here is a free software from NASA called Spice Enhanced Cosmographia, and they call this version Spice Enhanced because it is able to read all types of Spice kernels, and on macOS and Linux systems is able to execute scripts through Python to create high-quality animations. So this is the 39th video in this series. In this one, I'm going to be going over the Earth-centered inertial frames, which are the equatorial and ecliptic. So we'll be going over the Earth, equatorial, and ecliptic planes, definition of the reference frames basis vectors using those planes, the J2000 epoch, and then Earth spin axis precession. So first, let's define the Earth, equatorial, and ecliptic planes. The Earth equatorial plane is a plane that is normal to Earth's spin axis, where Earth's spin axis points from the center of the Earth to the North Pole, as is shown in the animation on the right here. And it's important to note that this vector is not fixed in inertial space. This is due to torques from the gravity of planetary bodies, which is mostly the moon. So the Earth's spin axis precesses with a period of 26,000 years. So roughly every 26,000 years, it'll do one 360-degree rotation, as is shown here in the animation. And recall that Earth's equatorial plane is where latitude is defined as 0 degrees, which is also shown in this diagram here as this line going around the globe. And the ecliptic plane is a plane of Earth's orbit around the Sun, and this plane is similar but not equal to the plane of the orbits of all the planets in our solar system, not counting Pluto. And if you're interested in learning more about why Pluto was changed to a dwarf planet from an astrodynamics perspective, I'll have a link in the description for the video that I made covering that. So now let's take a look at how Cosmographia would show that the Earth's spin axis is precessing. So right now we have the J2000 frame, which is the Earth-centered equatorial inertial frame. And then we're going to go ahead and pull up the IAU Earth frame, which is the Earth-centered Earth fixed frame in this case. So IAU Earth, and IAU is the International Astronomical Union that just defined this reference frame, which is the Earth fixed frame, where we have the x-axis is pointing at 0 latitude and 0 longitude here, just south of Ghana over here in Africa. So then if we go ahead and play the time forward at a very fast rate, we see that the Earth is spinning very quickly, but what we want to take notice is that the z-axis of the IAU Earth is going to diverge from the J2000 z-axis, which if we go fast enough, eventually it does, because this period is very long, 26,000 years, and here we're only at about to hit 2300, and we can see that this axis is actually diverging because the z-axis and the rotation axis of the Earth is actually precessing. So now that we know what those planes are, we can get to the definition of the Earth-centered inertial reference frames. So this is a slide from a document provided by the NAIF, and I'll have a link in the description to this document because it has a lot of very useful information on reference frames. So in this slide, they go over the definition of the EME 2000 or J2000 reference frame, where here the EME stands for Earth Mean Equator. So first we start by defining the x-axis of these inertial reference frames, where the x-axis for both of them are defined as the intersection of the equatorial and ecliptic planes called the vernal equinox. Now note that this is at a very specific time of 2000 January 1st noon TDB, where TDB stands for barycentric dynamical time. And this has to be defined at a very specific time because Earth's equatorial plane is not constant. It is precessing, as was shown in the previous slides. So if this frame was defined in, say, 2021, the x-axis would be pointing in a different direction, which would cause the y and z axes to also be in different directions. So now that we have the x-axis defined, we can get to the z-axis, where z-axis is defined as normal to the mean equator of Earth. It's supposed to be Earth at J2000 TDB, so at the exact same time, which is approximately Earth's spin axis orientation at that epoch. So what that means is that the z-axis is perpendicular to Earth's equatorial plane plane at this very specific time of 2000 January 1st, noon TDB. And the y-axis just completes the system, a right-handed system. So then the y-axis is z cross x, making that x cross y is positive z. And that's just a definition of a right-handed system. And now note that this is a definition of the Earth equatorial frame. And then if you wanted to get the Earth ecliptic frame, you just do a 23.4 degree rotation about the x-axis. So then this z-axis for the ecliptic frame would be pointing normal to the ecliptic plane, which would be roughly in this direction, which would mean that the y-axis is roughly in that direction. So it's just a rotation of 23.4 degrees. So now going back to Cosmographia to show how these two reference frames differ here, if we go to Spice Frames and type in J2000, we can get the ecliptic and the J2000 frames. And we can see as before that the x-axes are the same here, but we have that 23 degree rotation between the z-axis of both of them and the y-axis of both of them. And then we can also see if we pull up the grid, the lat long grid, that the x and y axes are in fact along the equator of the Earth here. So we can see the x and y axes of the J2000 frame, not the ecliptic, are along the equator of the Earth. So that's pretty much it for this video. Be sure to hit like and subscribe if you liked the video to help me out with the YouTube algorithm. And let me know if you'd like to see more Cosmographia animations in these videos, because it's the first time me showing how to do them. And just let me know if you think they're interesting. And in the next video, I'll be going to Keplerian orbital elements and how they are 313 Euler angles. So the 313 Euler angles, which describe the plane of an orbit with respect to the Earth-centered inertial frame, in most cases equatorial, where the first angle is a right ascension, a rotation about the z-axis. The second angle is inclination, a rotation about the x-axis. And the third angle is argument of periapsis, rotation about the z-axis again. So again, let me know any questions or comments, and thank you for watching.